a script. Much, much, much easier to read. Profile provider, 2 probes, profile and tick. Predicate that says, am I in the kernel, am I not idle? If those 2 conditions evaluate true, aggregate on the kernel stack. After 10 seconds, this probe fires. Truncate the aggregation, print it out, and exit. It's nice to write scripts. They're much, much easier to read. Another method for profiling the kernel, I'm not going to get into the details here because I'm running out of time, and I have a lot more, several more things I want to show you. The slides are available though, so you'll be able to, these are all downloadable, so you'll be able to get the slides to see this. So let me see. Actually, there is 1 or 2 things. Yeah, all right. So there is some stuff I wanted to show you here that gets to the methodology that you're going to use with DTrace. We won't worry for a second about the semantics of the script. You can figure that out just by sitting there with the documentation. What's more important, I think, is I want to give you another example of this drill down methodology that you use with DTrace to go from your first set of information to understanding more about what's happening on your system. So here I use this script to profile the kernel. And what does profiling the kernel mean? Does anybody not know what that means? It's okay if you don't. So profiling an application or profiling the kernel simply means determining what functions I'm spending my time in. Right? When I'm executing a piece of software, I'm executing code, I'm executing functions. When I profile code, I want to say, if I take a look at this code for 30 minutes, where did I spend most of my time and where did I spend the least amount of my time? That's what profiling software is all about. That's all it is. And the kernel is just another big piece of software. So profiling the kernel means I want to see what functions I'm spending time in the kernel. So this gave me an ordered list of output, and I could see that the hot function in the kernel is this function called mutex enter, which is the kernel function for getting a kernel mutex lock. Don't worry if you don't know what a mutex lock is. It's just a synchronization primitive. For the purposes of this example, you don't need to know what it is. You just need to see that the output of DTrace using the count aggregation showed me that my hot kernel function was use mutex enter. I hit it 17,000 times while I was collecting this data. The next most frequent function I only hit 5,000 times. So I want to drill down on that. Where's mutex enter coming? So digging deeper, I use DTrace and I say, DTrace, light up a probe called mutex enter for me. And lo and behold, in the top line I say, oh, there are no probes called mutex enter, sorry. So I say, well, son of a gun, I need to chase this mutex enter function. Let me take a look. So I'll use my, I'm a Unix guy. I know how to do pattern matching in Unix. I'm going to use dtrace-l, list all the probes, and I'm going to say, do I have any probes that have the string mutex enter in them, right? And I do. I have 3 probes that have the string mutex enter in them. They're part of a provider called the lockstack provider. So now I'm going to say, okay, lockstack provider, turn on all the mutex enter probes, and every time that probe fires, which means what? It means I called the mutex enter function. When that probe fires, it means I called that function, get me a kernel stack trace. So this is showing me, basically, where in the kernel I'm making all these mutex enter calls. And you can see, well, you could email this to somebody, but if you know how to look at a stack frame, take a minute to look at it, you can see, oh, while I was collecting data 1,893,000 times, I called mutex from this IP SQ enter. That sounds like a networking thing to me. Oh yeah, look, I did a sys call, I did a write system call, and I got this thing called sockfs. That's a socket function, so I know I'm in the network. So it looks like I'm writing to the network a lot. And then, oh look, I did a read system call through a socket. That's a network endpoint. And I did a bunch of other stuff here that I'm not going to decipher. But that's okay. That's okay. Give yourself a minute to look at those stack frames, because even if you're not a software developer and you don't know what a stack frame is, you can glean information from it. You could see I did writes. You could figure out that you were writing to the network and reading from the network. And even if that's all you get out of it, you've actually learned a lot about A, what your system is doing, and you know where all these mutex enter calls are coming from.
I want to ask, mutex enter showed up as a function when you were profiling.
Right.
But it's not listed on the function boundary trace provider.
Right.
What's the reason for that?
Great question. Ask me when we're done. The summary answer is because that function is it's an assembly lead function in the kernel, and there are some functions in the kernel DTrace can't instrument, and that's one of them. Okay. So I just learned a lot about where this mutex enter thing is going and what my system is doing. And now I said, okay, this piece of data showed me I'm doing a lot of write system calls. Where are all these write system calls coming from? Now I'm going to use the syscall provider. I was doing a lot of reads and a lot of writes, right? Okay, you guys with me? Cool, okay. So now I'm going to say, all right, where are all these reads and writes coming from? So I'm going to use the syscall provider. I'm going to light up the entry point of the read system call. I'm going to light up the entry point of the write system call. And I have a predicate that says, I'm not going to tear this down because I don't have time. What that predicate is basically saying is if the target file system for the read or the write is the socket file system, which means it's a network read or write, then I'm going to take this action. So basically I'm saying every time I do a read or write system call, if it's a network read or write, give me the process name and the PID and count them up. And you can see that I have, big surprise, a bunch of Oracle processes and these other processes that are part of the workload running on my machine called RWDoIt, very clever name, whoever wrote it, that are generating all these reads and write system calls to the network. So now I know that A, my system is doing a lot of network activity, and I can see which specific processes that are running on my machine are actually generating the network load. And now I can say to myself, okay, I wonder how much traffic I'm actually generating. Now this is really, really slick. I love this. It's just going to take me a minute or two to get through. I'm lighting up the same probes. Entry point to the read and the write system call. We good with that? Two probes, read, write. I'm using the same predicate that says, are the targets of my read and writes the socket file system, which means they're network. Cool, okay. And now in my action, I'm doing something that you haven't seen before. I'm using an aggregating function called sum. Remember that I said DTrace has about a half a dozen or so aggregating functions? You've seen me use count most of the time. Sum is a different aggregating function, and what it does is it does a rolling arithmetic sum of whatever I pass it as an argument. Now in this case, I'm passing it arg2. Now, what's arg2? Now this gets to, you know, how long have you been a Unix geek kind of thing, right? And this gets to, remember, every probe in every provider has arguments that you can use to get data. What those arguments are going to be specific to the probe and to the provider. The only way to know is to read the documentation. In the case of the syscall provider, arg0, arg1, arg2, arg3 are all the arguments that get passed to the system call. If you're a Unix programmer, when you write a Unix program and you make a system call, the read system call takes a file descriptor, a memory buffer, and the number of bytes to read as arguments. The system call takes a file descriptor, a memory buffer, and the number of bytes to write as an argument. arg2 is the third argument passed to the read and write system call, which is, in the case of read and write, the number of bytes that I either want to read or that I want to write. So basically what I'm doing is I'm using DTrace to tell me how many bytes am I reading from the network and how many bytes am I writing to the network. How much throughput am I generating over my network pipe on my system. It's a very, very powerful bit of information that's being extracted with a relatively simple DTrace command. Now, how do you know what arg2 is when you're using the syscall provider? Man minus S2, the name of the system call, right? There's over 200 system calls at Select.